Ana, eu acho que você já pode abrir seus slides, se você quiser começar.
Vou compartilhar aqui.
Tá. Bom, deixa eu agradecer a participação de todo mundo nessa sessão. Nós vamos começar com o trabalho da Ana Santos, logo depois o trabalho do Kazuhiro, e depois fecho a sessão. Acho que eu estou vendo aqui, não tem ninguém que é falante de língua inglesa, né? A gente pode apresentar em português. Acho que não tem problema.
Fica a critério de vocês.
Certo. Acho que podemos apresentar em português. Bom, fica a critério de cada um dos panelistas. Ana, você tem a palavra.
Wait a second. We need to check if Kazuhiro is okay with Portuguese.
Oh, sure. Yeah. Sorry.
Oh, I'm not okay with Portuguese. Sorry.
That's what I thought. I
I'm
think
so sorry.
Do it in English.
Oh, sorry, Kazuhiro.
No, but
problem.
if you want to do your presentation in Portuguese, that's fine. I can.
No, we'll do it. We'll do it in English. Don't worry.
Okay.
No problem.
Thank you, Eduardo, for reminding me.
Thank you.
Okay, so Ana, the floor is yours.
Okay, so hi everyone. First of all, I'd like to thank you all for being connected today and for the opportunity to present our work for this audience. This paper is part of my PhD thesis, and it's a joint work with Lorenzo and José Leno. The title of our paper is Dynamically Consistent Objective and Subjective Rationality. So we motivate our problem as if there is a group of individuals acting as a decision maker. For instance, think of a group of epidemiologists advising a prime minister about the best policy to fight the coronavirus. In the beginning of March, due to the lack of data and higher uncertainty about the number of infected people, some epidemiologists may have assigned a high probability to a pandemic scenario with several 100,000 of contaminated people by the coronavirus in all Europe, while others may have thought that such a scenario was not as likely to happen. Suppose they have to choose among two policies. F is lock down the population and G is herding immunity. Assume that each expert or each member of this group is represented by a subjective expected utility preference, and they share the same affine utility index. So U does not depend on the expert. It's reasonable to think that different experts assign different probability distribution to possible scenario. For example, expert 1 has probability P1 over the possible scenarios. And he prefers F to G if and only if the expected utility of F is greater than the expected utility of G under his probability distribution P1. And C, it denotes the set of all experts and represents the heterogeneity in beliefs among the members of the groups. Okay. If everybody in the group agree that F is better than G, the decision is unanimous, meaning that the expected utility of F is higher than the expected utility of G for all probability distributions in the set C, or for all experts. However, it's not sufficient that it is sufficient that one expert rank G above F to break the unanimity. So all experts have a veto power. When they disagree, it's not clear which policy the decision maker should implement. In this situation, especially when uncertainty about different scenarios is high and there are scenarios that can lead to catastrophes, several authors suggest to adopt the precautionary principle. According to this principle, a policy should be evaluated to the opinion of the most pessimistic expert. Gilboa, Macchione, Marinati, and Schneider offer an axiomatic foundation support the use of the Maximization rule of Gilboa and Schneider in order to complete the unanimity rule when full agreement among experts does not hold. They propose an axiom called default to certainty that favors certainty if there is lack of unanimity. So in our context, default to certainty behaviorally justify the identification of the Maximization rule with the precautionary principle. And we follow their approach of a decision maker characterized by two binary relations, capturing two notions of rationality. The objective rationality, denoted by the preference star, captures the unanimity rule, and the subjective rationality preference hashtag captures situations where the precautionary principle applies with the Maximization representation. And the policy which, with maximal expected utility under the worst case probability should be chosen. Under this rule, the decision maker does not feel embarrassed with the decision because others cannot convince her of being wrong. So consider the classic Ellsberg type example with an urn with 90 balls, 30 of each are red, and the remaining are green, are either blue or green. A group of experts with the same affine utility index can be identified by the set C. Okay, so the set C gives 1/3 probability for the ball being red and the remaining probability for the ball being blue or green. And suppose they have to choose between the two acts, F and G. So F pays 10 if the ball is red and G is red or green, and G pays 10 if the ball is blue or green. Okay. The experts cannot compare F and G using the unanimity rule. For instance, for this P1 and this P2 that belongs to the set C, they disagree. So the expected utility of F is greater than G for P1, and the expected utility of G is greater than the expected utility of F for P2. If we take the completion of the preference star applying the precautionary principle, we find under the Maximization representation that G is strictly better than F. Oh. Vocês estão vendo minha tela?
Not anymore, Ana.
Ah, agora sim, né?
Yeah, got back.
Okay, thank you. Deu problema aqui. So, okay. So, however, if we introduce an intermediary period of partial resolution of uncertainty, meaning that the experts know today that they will have some information tomorrow, this decision rule may violate dynamic consistency. This means that decisions taken today may be regretted tomorrow, no matter how information is revealed. The main contribution of this paper is to provide a refinement of the concept of objective as subjective rationality so that dynamic consistency is preserved in a model with a period of partial resolution of uncertainty. The main idea is that the group of experts should take into account today the structure of information that they might face tomorrow when uncertainty will be partially revealed. We impose some conditions on the objective preference, on the unanimity rule, in order to avoid regret on the subjective preference, the Maximization rule. We propose two axioms, Axiom ex ante and ex post coherence, that allow us to derive the coherent precautionary reassessment of the unanimity rule. I will be more precise later on what is a reassessment, but it's basically a revision, okay? So the idea is that we must add as many experts in the group as possible in a coherent way to avoid regret caused by violations of dynamic consistency. Our analysis offers a novel behavioral characterization of rectangular set of prior and a prescriptive way to aggregate opinions in order to avoid regret. So just talking a little bit about the framework. So F is the set of states of nature. For instance, the virus is severe, mild, or innocuous. The DM doesn't know which state of nature will occur, and she has preference over acts that are handle variable. An event is a subset of the states, the set of states of nature. And given an event E and two acts F and G, we define the act FAG by the act that gives F of S if S is in E and G otherwise. If experts know today that they will have some information tomorrow, there is partial resolution of uncertainty. This is formally described by a partition of the state space of S with an event such that the probability of each event in the partition is strictly greater than 0 for all events in the partition. We denote preference E, the conditional exposed preference for a given event E, then conditional preference of an unconditional preference. And C of V denotes the set of prior by prior based on the updates of C given E. So recall our notation for the unanimity rule. We use the preference star, and its completion when we adopt the precautionary principle is the preference hashtag. This definition of dynamic consistency is well known in the literature and relates the unconditional preference with the conditional preference. It basically says that the DM should consistently carry out plans made ex ante. The unanimity rule is always dynamic consistent, but in general, these preferences are incomplete. Using the precautionary principle to complete the conditional maximum rule, the conditional unanimity rule with a maximum preference, possible dynamic inconsistencies may arise. So returning to our example, let's add the intermediary period of partial resolution of uncertainty represented by the partition P. So in the intermediary period, the decision maker will learn whether the ball is green or not. The full Bayesian update of the set C gives us the set C of G and the set C of RB. If the ball is green, the two acts are equivalent and the DM is indifferent between acts F and G. Otherwise, he cannot compare. So under preference conditional on the ball being red or blue, the acts F or G are not comparable. The completion of preference star using the precautionary principle gives us that F is strictly better than G conditional on the ball being red or blue. And dynamic consistency would imply that F is better than G, which is a contradiction of what we saw before, that G is strictly better than F, unconditionally. Dynamic consistency is viewed as a property of preference fundamentally related to rationality, therefore it is reasonable to require it for subjective rational preference. We propose a modification of the unanimity rule in order to avoid possible violations of dynamic consistency when the maximum rule is considered. So we propose a modification on the unanimity rule that should satisfy two conditions. First, it's a reassessment, meaning that it cannot reverse rankings given by the original unanimity rule, and no comparisons and new comparisons cannot arise. So the preference to star, which is this reassessment, is more incomplete, meaning that more experts with veto power are added to the group. The second condition is that the modified preference must be coherent, meaning that it coincides with the original unanimity rule whenever violations of dynamic consistency cannot occur. So basically, the first condition gives us that we should add experts to the overall decision, and the second condition says which experts we can add to the group. What is the condition to add experts? Okay, so must be in a coherent way. So X0 denotes an outcome that gives zero utility, and we fix a partition of events, and the conditional probability star and the conditional probability to star denotes the dynamically consistent updates of the preference star and two stars. Okay. So as I said, coherency imposes some conditions on how new experts are chosen. No possible violations of dynamic consistency if y is better than x e x0, or if x is better, x e x0 is better than y, or if f is better than g conditional on e, all for the unanimity rule. Okay, so ex ante coherence says that preference to star should rank bets over events in the partition in the same way as the preference star. And ex post coherence states that the preference to star conditional on e should agree with preference star conditional on e for events in the partition. So given a partition, we say that the preference to star is the coherent precautionary reassessment of preference star if preference to star is the most incomplete unanimity rule, such that the two preferences star and to star satisfies ex ante and ex post coherence. Most incomplete meaning that we add as many experts as possible. Loosely speaking, if you do not impose the condition of being the most incomplete unanimity, preference to star will be subject to the same issues of dynamic inconsistencies as the original preference star, once we take the corresponding completion with a Maximization representation. So this theorem is the main result of our paper. So given a partition, the preference to star is the coherent precautionary reassessment of preference star, if and only if is represented by this rule here. Okay, so f is better than g on the preference to star, if and only if we make a weighted average of the conditional preference in this way, and this is true for all probabilities in the set C. Okay, so here giving so just giving an example, the new experts are constructed for the old ones in the following way. First, we fix n+1 probabilities in the set C. For simplicity, we denote pi, the probability assigned to the set EI, to the event EI. For an act F, we compute the expected value through the Bayesian update with respect to EI, and these expected utilities are aggregated to convex combinations in which the weights are given pi p0. Okay, so basically, we take all experts in the set C, we compute the Bayesian update for each event in the partition, compute the expected utility of the act F, and then make a convex combination using another probability C in the set C. Okay. The rectangular rule of the set C for a partition P is obtained by considering all convex combinations of the conditional Bayesian probabilities, with weights given by the unconditional probability. This definition is based on the previous contributions of Sarin-Evaker and Epstein-Schneider. So a corollary of our results shows that our results offers a novel behavioral foundation for a rectangular set of priors based on the interaction of two unanimity preferences. So the preference to star may be represented by a unanimity rule over this rectangular set of C. Okay. And corollary 2 together with theorem 2, our main result, gives a new behavioral characterization of rectangularity and dynamic consistency. So if we have preference to star, the coherent precautionary reassessment of preference star, if we take the maximum precautionary completion of this new unanimity rule, then the pair of the maximum rule satisfies dynamic consistencies. So going back to our example, if we compute the coherent precautionary reassessment preference to stars with respect to the preference stars given the partition P, we have this rectangular set of C, and its preference to star is ably represented by the same U and the rectangular set of prior. the acts F and G are not comparable with respect to this new unanimity rule. But if you compute its completion, considering the maximum representation, we get that F is better than G under this the maximum completion of the new unanimity rule. And no dynamic consistency problem arises. Actually, we obtain that F is better than G unconditionally, and F is better than G conditional on the act being red or blue, or if the ball is green, okay? So to conclude, the unanimity rule says that a policy F is preferred to G if and only if every expert or equivalent, every probability measure assign higher expected utility to F rather than G. If two experts disagree, this rule is unable to tell which policy is better. When a decision must be taken, several authors suggest to compare policies to the precautionary principle, meaning that the policy with the highest minimal expected utility should be chosen. As we saw in the example, this rule may generate possible dynamic inconsistency when an intermediary period of partial resolution of uncertainty is added. In order to avoid that, we provided two axioms that modify the original group of experts. We derive a new unanimity rule called the coherent precautionary reassessment. And the new opinions are formed by taking convex combination of the expert updated belief using the Bayes rule. This makes the completion of the new unanimity rule dynamically consistent. So that's it. Thank you for, if you have any question, I can answer now.
Thank you for your presentation, Anna. We still have time for a round of questions. Are there any questions?
Okay, so maybe this is a basic question, but there's something I didn't quite understand. When you first introduced the partition, so you have a specific information structure, right? Like that people can learn this specific partition. Now, is the representation dependent on specifying this partition, or would it change if we change the partition, or is there something connecting how the representation works for different partitions?
Okay, thank you, Henrique, for your question. Yes, so in our model, we fix a partition. So we fix a partition, and as we can see here in the rectangular rule representation, here, the set C depends on the partition. So the decision maker should know today what is the partition that he may face tomorrow, okay, in the next period. And given this partition, we can solve this dynamic inconsistent problem in this setup of objective and subjective rationality. So if the partition change, then the decision might change also, because the rectangular set change, and this rule here, the result from this rule here may also change with the partition. So the partition is a primitive of our model. So we are fixing the partition in the beginning. Okay. Thank you for the question. So I stop sharing my tela.
Okay, thank you very much for the presentation, Anna.
Thank you.
Kazuhiro, you may want to set your slides for presentation if you want. We still have 5 minutes, but if you want to start a little earlier, no problem. Can you share your screen?
Yeah, I'm trying. Give me a
Okay.
second.
Sure.
Hi, Kazuhiro. Do you have your slides open on your screen?
Not yet.
Oh, okay. Because all we're seeing is a dock screen.
Right. So okay. There you go.
Good.
All right. So okay. So let me start. Okay. In this paper, I study behaviors of rational decision maker who is in a strategic situation. So he's in a strategic game with some other decision makers. Assuming that as an outside observer, we do not observe these players other than the decision maker. So we see the decision maker's strategic choices, but we don't necessarily observe the second or third players' strategic choices.
But do we know how many players there are, and do we know what their actions are?
It depends on, so depending on assumptions on number of these unobserved players and or the set of strategies that they use, whether we observe the set of strategies that they use or not, I consider different models depending on assumptions on them. So such situations like that can happen in following scenarios. For example, so there's a decision maker who is in the game, but these other players, other than the decision maker that we are observing, have privacy concerns, and they do not disclose their choices to us. That's one scenario in which this can happen. The other scenario is that the decision maker is delusional. He's facing some choice problem, which is it's not strategic, but he has some enemies in his mind and treat it like a game, and ends up playing a strategic game. So when the decision maker makes strategic choices strategically, their choice may be observed as violating weak axiom or rebuild preference. This is a simple, direct consequence of the fact that Nash equilibrium correspondence can fail up. To see that, let's look at this game example on the left. So there are two players, player 1 and 2. Player 1 has 3 strategies, X, Y, Z. Second player has 2 strategies, A and B. Clearly, there are 2 equilibria, XA, so this one is one equilibrium, and the ZB is another equilibrium. Now, suppose strategy Z becomes unavailable, right? Now we are looking at the smaller game where player 1 uses X or Y, player 2 uses A or B. There are 2 equilibria, XA and YB. So if we observe, so assuming that they play Nash equilibria, and if we observe only player 1's behaviors, then we would observe him choosing from X, Y, Z, he would choose X and Z. And from X and Y, we observe him choosing X and Y, which is a violation of weak axiom. And same thing can happen even if the game is more structured. For example, the game is symmetric. So that's the example on the right-hand side. This game is symmetric. Each player has 3 strategies, X, Y, Z. And there are 2 equilibria, XX and ZZ. If Z becomes unavailable, then there are 2 equilibria, XX and YY. Again, if we observe player 1's behavior, then he would choose from XYZ, XZ, and then from XY, he chooses X and Y. So although even if player 1, the decision maker, is fully rational, his behavior, his choice behavior may violate WAP. So this paper asks the following questions. How does player one's behavior look like? And I asked this question. I studied this using 3 different models from rebuild preference perspective. So these models are different in terms of number of unobserved players, which I called phantoms. So these phantoms are the players that the decision maker play a game with. They may not exist. They may exist only in his mind. So these models differ in number of phantoms, and the equilibrium concept that I use, and in terms of whether we observe phantoms set of strategies or not. The first one, there's one phantom, and we don't know the set of strategies for that guy. Second model has one phantom who is symmetric to the decision maker, and we will look at symmetric equilibria. And the last model has, I allow multiple phantoms. Okay. So here's some notation that I use. X is the set of alternatives. This set can be finite or infinite. Script A is it's a collection of choice problems. A choice problem is a non-empty subset of X. Script A can be strictly smaller than the power set of X minus empty set. So the data set can be partial. And C stands for a choice correspondence or a choice function. So C is the data set that available to me. So X corresponds to the set of all the strategies available, all the strategies for the decision maker. Okay, so here's the first model. As I said, there's one unobserved player, a phantom, and phantom has a set Y of strategies. We don't observe set Y, okay? And for each choice problem S, the decision maker uses set S as the set of strategies for him. So set S is the feasible strategies. And decision maker plays a game against phantom. Phantom uses strategies in set Y. And they play Nash equilibria. So the decision maker's choice that we observe contains all the equilibrium strategies. So alternative X is chosen if and only if there's some strategy for the phantom Y, and the XY pair is a Nash equilibrium of the game where player 1 uses strategies in set S, second player uses strategy in set Y, where they have, both player has fair functions. So there
Y is unknown to player 1, right?
Player 1 knows Y. We don't know Y.
Okay.
Yeah. So there are 3 parameters in this model, right? Set Y, it's 3, and the pair of functions U1 and U2. So this gives us a lot of freedom, and at glance you might think, oh, okay, anything can happen, but it turns out there's some testable implications, which is what is called the alpha axiom, Sen's alpha axiom, which says if choice problem S is smaller than T, then whatever chosen in T that is still available in set S must be chosen. So it's easy to see that the model satisfies this condition, right? So if X is an equilibrium strategy in some larger game, which means there's some strategy Y for the phantom and XY pair is an equilibrium, then, and now the decision maker's strategy set becomes smaller, but X is still available, then XY pair remains an equilibrium in the smaller game. So this phantom strategy doesn't change in this model. So it stays, it's Y. It just, first, decision makers' strategy, set of strategies can vary. It turns out that's the only restrictions that the model imposes on the data set. So theorem 1 says, let's say C is a choice correspondence on collection of choice problems, then it satisfies alpha if and only if there's some set Y and some pair of functions so that the choice from set each choice problem is the collection of equilibrium strategies. It's hard to talk about uniqueness of this representation, and I don't, at this point, I don't know how to talk about uniqueness. The representation is not unique at all. And there are many ways we can construct set Y and pair of functions. Let me give you one possible way of constructing Y and pair of functions. So you can take Y equals to script A. Y can be the set of all choice problems. And okay, sorry, for that let me assume that script A contains all the choice problems. Okay, script A equals to the power set minus empty set. Now you can take Y equals to that script A, Y equals to script A, and pair function for player 1 for the decision maker is the indicator function of X, sorry, U1 of XS. XS is a one strategy profile. X is the decision maker's choice. S is the phantom's choice. The U1 of XS is equal to indicator function of X minus S evaluated at small x. And the second player's payoff function can be the indicator function of, so U2 of XS equals to the indicator function of C of S evaluated at X. So basically, player one deems everything indifferent in his choice set, and the second player kills the indifference so that the representation holds. But that's just one way of one construction. There can be many other. If we want these pair functions to be continuous, we can do that under some technical assumptions. For example, we can assume X to be a compact metric space, and we can assume that the set of choice problems is equal to the set of all compact, no-empty compact subsets of X, which is endowed with the Hausdorff metric, and impose standard upper Riemann continuity for choice correspondences. Then we can show that a choice correspondence on these compact choice problems satisfy alpha axiom and upper Riemann continuity if and only if there's a compact metric space Y. This is the set of strategies for the phantom, and two continuous pair functions. And we have the desired representation. So let me give you some examples of choice correspondences that admit this representation, which is equivalent to the choice correspondences that satisfy alpha axiom. So sanity check first. Example one is rational choice, preference maximization. Preference maximization is equivalent to WAP, which implies alpha axiom. And of course, preference maximization can be written as a game in an obvious manner. The phantom has single strategy. He doesn't do anything, and the decision maker just maximize. Second example, choice functions. Choice functions satisfy alpha axiom if and only if it satisfies IIA. So it satisfies alpha if and only if it's preference maximization. So if we want anything interesting, we need to look at choice correspondences instead of functions. Slightly more serious example. Let's look at example 3, path independent choices. Path independence refers to the following condition. Choice from union of two problems, S union T, is equal to the choice from set S union, choice from set T. Choice from S union T must be equal to choice from S union choice from T. Q acceptance rule, which is popular in, I think, matching school choice, is known to satisfy this condition. Q acceptance rule consists of a ranking over alternatives and capacity Q, and the decision maker choose top Q alternatives according to the ranking. And if there are only less than Q alternatives, he chooses everything. It's when X is finite, it is known that path independence is equivalent to the following representation. The decision maker has finitely many utility functions, VIs, and choice from set S is equal to the union of all the maximizers of these finitely many utility functions. given that, we can write it like a game. Just take y, let's just let y equals to the set of indices, 1 from k. K is the number of utility functions that we need to represent passive dependent choice like this manner. And the second player's payoff is constant. First player's payoff is given by this. So when player 1 chooses x, phantom chooses index I, then his utility, his payoff is pi of x. Another example is a threshold model. Threshold model consists of a utility function and a threshold function delta. And x is chosen if and only if the utility for alternative x plus threshold, which depends on x and choice problem itself, exceeds or equal to the maximum utility that one can achieve on set this. This model satisfies alpha if this delta function is decreasing with respect to set inclusion. So we can write this as a game. Unfortunately, I don't know, I couldn't find a nice way of game representation for this model. So I cannot give you a nice game representation now, but I'll deal with the special case of this model in the next model. Okay. So that's the first model. Here's the second model. In the second model, there's one phantom, and the phantom is symmetric to the decision maker. So for each choice problem S, decision maker and the phantom uses set S as the set of strategies, and their payoff functions are symmetric. And I assume that they play symmetric equilibria. So the observed choice consists of strategies X such that XX pair is a symmetric equilibrium of the game. So set S is the set of strategies. U here, of course, is the payoff functions for the decision maker. And because the game is symmetric, the phantom's payoff is given by a symmetric function to U. So again, it's easy to see that the model satisfies alpha axiom. It actually satisfies a condition slightly stronger than alpha. There's a condition called weak y. Y stands for weak axiom revealed non-inferiority. Weak y says, say we have an alternative x in S, and for every y in S, there's some choice problem which contains x and y, and x is chosen. Then x must be chosen from the original set S. Weak y was introduced as one of the conditions that characterizes maximization of pre-orders. So it says, that x is chosen when xy is available, means y does not dominate x. And if it is the case that every y in set S, each y in S does not dominate X, then X must be chosen. And it turns out that the second model is the only restriction that the model imposes on data is weak one. So choice correspondence satisfies weak one if and only if there's some payoff function, so that the choice consists of strategies in a symmetric equilibrium. And here are some, I see. So when X is finite, we can simplify weak one. We can use a condition called expansion, which says if X is chosen from S and T, then X should be chosen from union of S and T. And when X is finite and we observe all the choice problems, then weak one is equivalent to alpha and expansion. So choice correspondence satisfies alpha and expansion if and only if it can be written as a symmetric game. And here are some examples of choice correspondences that satisfies weak one. So when X is finite and all the choice problems are available, then it is known that alpha axiom and expansion is equivalent to maximization of complete acyclic relation. So the model is equivalent to maximization of complete acyclic relation. And that's one example. And second example is maximalization of preorders, which is known to satisfy a condition called Warney, which is stronger than weak one. And by using multi-utility representation of a preorder, we can construct a game representation. Another example is an interval order. This is a special case of threshold model where the threshold function delta is independent of choice sets. So X is chosen if and only if utility of that alternative plus delta X, X is the or equal to the maximum utility level. If you want to write this as a symmetric game, we can use the following payoff function V. So when the decision maker and the phantom uses the same strategy, they get payoff UX plus delta X, and otherwise they get just UX.
I'm sorry, Kazuhiro, you have 2 minutes if you would like to wrap up. Now would be the time. Sorry to interrupt you.
So the third model consists of multiple phantoms. So there can be arbitrary number of phantoms. They use set S as the set of strategies. They play Nash equilibria. It turns out this model has no testable implications. So every choice correspondence can be written in this manner, which may not be surprising, I guess. I think it's more interesting to consider this model when there's some bound put on the number of phantoms, but I couldn't prove anything on that front. I trying to characterize this model where there's only one phantom, and that special case has some interesting examples, which I'm going to skip. here's some application. I can provide the representation, alternative representation for some famous models of bounded rational choice, which is called rationalization and rational shortlist method. I can basically represent them as selection from equilibrium strategies. So that so that's about it. Thank you.
Thank you, Kazuhiro. We don't have enough time for questions, so I'm gonna jump to my presentation, and I'm gonna share screen with you. Just a sec. Right. So, can you all see the slides? Can you see the pointer?
Yes.
Yes.
Okay, thank you. Right, so let me start. Well, people follow the wisdom of crowds. We buy popular brands because we believe that popular brands somehow indicate quality. We buy books on New York Times best-selling list, and a small amount of people withdrawing money from banks could trigger a huge bank run. So because people follow the wisdom of crowd, manipulating crowd behavior is the ultimate goal of some other people, politician, financial analysts, to name a few. So this paper is about crowd manipulation through dynamic information disclosure. And I have a very simple, stylized environment between a sequence of short-term investors and financial advisor. Short-term investors would like to invest in an asset of fixed quality, but unknown ex ante, and they may get information through the advisor. The advisor is patient, so he discounts future payoffs, but he doesn't care about investors learning the quality of the return of the asset. So there might be some conflicting interests here. And he commits to a public information rule. You can think of this public information rule as some sort of a study about the quality of the asset, in which he has to be public about the results of the study, but when to disclose and how clear to be, it's his strategic choice. So that's why I say that he must be honest, because he has commitment, but he can also be strategic. And the advisor has to deal with private information. Investors also get private information everywhere, and the market never forgets. Current investors observe past investment choices and pieces of advice. Because they observe past, because they might choose according to their private signal, observing past actions might lead to some inference about the return of the asset. So every time that an investor chooses according to his private signal, there is some sort of information externality, right? So for this talk, I'm going to focus on 2 questions for which the paper has some interesting answers about it. So the first question is, how does an info designer change the dynamics of the market beliefs? So even though there are conflicting interests here, I showed that there is a social benefit with an info designer, because one of the informational cascades, public belief sets for which investors would choose an action no matter the private signal, it shrinks to a singleton. And if the return is high, only investment cascade arises, which means that only good herds arise, only a good herd arises in this specific setting. This will not be possible in a standard observational learning model without an information designer. And if the return is low, there is complete learning with some probability eventually. And the second question is, to extend, should the designer allow some sort of info externality? In other words, to which extent should the designer encourage investors to choose according to their private signal? I can be able to give a simple condition if I restrict the private information structure of a class that is widely used in economics and statistics, the log concave private info class. And I show that it depends on how rare are private signals contrary to investment behavior. And I show also that this optimal info externality is mostly a short-run phenomenon, in a sense that an infinitely patient advisor would be just as well not ignoring completely this information externality. Okay, so there's an asset delivering a fixed return. It can be a low quality asset or a high quality asset with equal prior probability. Short-term investors, they arrive and they choose whether or not to invest. They would like to invest if and only if the return of the asset is high, but a long-lived advisor discounts future payoffs, and it gains one whenever investors invest. There's private information in the market, meaning that each investor might get a realization from a random variable that is independently and identically distributed, conditional on the ad return. Because investors are Bayesian, private signals generate private beliefs about the return being low. And because we have private signal distributions, we will have private belief distributions. And we'll also have an unconditional distribution about private beliefs. And it's sufficient for my results to assume, to work with the unconditional distribution G. I will assume that it's absolutely continuous, then it will ensure that it will have a density, and the support is going to be a closed interval, and this support will be common between the two conditional distributions of private beliefs. And I will assume that without any information, investors choose according to their own private signals, which means that the prior belongs to the interior of the support. Private beliefs will be called bounded if it is a proper interval of 0 and 1, and it will be called unbounded otherwise. So investors, they combine the inference from private signals, which they get private beliefs, and inference from a public belief about the return being high. Because they are expected utility maximizers, they will invest if and only if the private belief is lower than the public belief. Of course, future investors and the advisor, they don't know what was the realization of the private signal. And because they don't know, they have to infer what will be the investment probability ex ante, and they are given by alpha high, alpha theta. I can show that we can completely describe those unconditional investment probabilities as a function of the private information structure alone. Okay, so the advisor commits to a public information rule, which consists of a message space, conditional probability messages over the message spaces for every public history of actions and messages, and also for the quality of the asset. Remember that I am assuming commitment of my advisor. So every public history leads to a public belief. Every message realizations at every public history will lead to an induced belief because investors are Bayesian, and the expected value of all induced beliefs at a given public history must be equal to the public belief generated by those history, by this history. This is called Bayes plausibility in the literature. And here's the timing of events in terms of the beliefs in this game. There are three: the public belief, induced belief, and the private belief. The advisor chooses a public information structure. Some investor T arrives, observes a public history, generates a public belief. Then the designer, my advisor, sends a message induces some belief. Then the investor will combine induced belief with the public one to take a decision. The next investor will observe the investment choice and the pass message. And because the investor in T may choose according to his private signal, investor T plus 1 will may infer something from investor T's action. There will be two possible belief updates because there are two actions. It could be a belief update after a non-investment decision. Then this is gonna send the public belief down, and there will be a public belief inference from investment decisions. This will increase weekly the public belief next period. Okay, and because they are Bayesian, they are just doing some Bayesian inference here, right? Okay, so just to give an example, suppose that the private information structure is uniformly distributed, and I can completely summarize how informative private information could be using the sigma. Sigma close to 1 means that private beliefs are very bounded. You cannot get much information privately. And if sigma is pretty close to 1, private information is very unbounded. You can get a lot of information out there, right? So it is straightforward to compute investment probability and the transition functions. They will be useful later on. What I want you to guys see is that there are some regions for which investors are going to take some degenerate decisions. And that happens because any private belief realization will make them invest or not invest for sure. When this happens, the next investor will not learn anything from past investor, so there is no belief update. Okay, so let me argue that we can describe advisor's problem as a Markov decision problem, and only beliefs matter. I have shown that for any information rule generates two stochastic processes, public beliefs and induced beliefs, that satisfies Bayes plausibility and a well-defined transition functions. Well, the converse also holds with some just some technical modifications from a lemma in Jeff Ely, 2007, which says that any stochastic process of beliefs satisfying conditions 1 and 2 can be generated by an infer rule, which is very special. It is special because the message space is the belief space. So I'm literally saying to the investor what beliefs should they hold, and the distribution over induced beliefs depends only on the current public belief. So with that in hand, we have a Markov decision problem because the beliefs account for the state of the system. The initial state is the prior. The actions that the advisor can perform here are distribution of posteriors, and yes, they must be feasible, which means that they must belong to the set of plausible distributions. The transition probability among beliefs is given by this transitional kernel, and the period by period reward is just the investment probability, right? Because I can write that as a Markov decision problem, all the nice properties about standard dynamic programming hold here. Specifically, I show that the right-hand side of this equation is actually an operator, which is a contraction and could be achieved by a fixed point. For every possible realization of a public belief, there is a distribution of posterior that leads to the maximum. And most important, the optimal value function is going to be concave. Just a technical reminder here, the literature on dynamic animation design usually assumes that there's only one transition probability from one belief to another belief. So here I extend a dynamic concavification. This is the name of the algorithm. So I extend a dynamic concavification algorithm to account for multiple transitions, and each transition is indirectly affected by the message of the advisor. So are there any doubts so far? If not, I'm going to talk about the belief dynamics. So suppose that the public belief dynamics hits the set of beliefs which is at the right of the support. Well, investors will invest no matter the private signal. There is no reason for the advisor to provide additional information. So the belief processes converges and learning here eventually stops. But what about when the public belief hits the left-hand side of the support? Well, if private beliefs are unbounded, there's not much we can do. But if the private beliefs are unbounded, there is clearly room for intervention, because not saying anything will lead to a zero payoff today, but it will also lead to a zero payoff tomorrow, because there will be no belief update. So I show in the next proposition that for any possible public belief, which is in the non-investment cascade, the best thing that the advisor can do is use his informational power to be very assertive about the return being low, which means putting beliefs at the 0 point. But this is important for him to have enough probability to induce beliefs outside, with some probability, the non-investment cascade set. Okay? Right. So we have a dynamic Markov decision problem with two observing sets. One is a singleton and the other is the investment cascade. I can show that even if persuasion here, the public belief process continues to be a martingale, and being martingale, it converges almost surely to a random variable. So the next step is showing that the support of this random variable must be contained in the absorbed sets of the game. This is what I show. And for those of you who are familiar with the observational learning models, the proof of it is quite standard, but I have to account for the possibility of the advisor generating new information that could trigger the belief process out of the cascade sets. What I show is that in those absorbing sets, there will be no additional disclosure, so the belief process eventually stops there. And an interesting implication is when the private beliefs are bounded, because without intervention, it can be shown that bad herds may arise if the return is high. This will not be the case here, because Bayesian investors cannot be dead wrong about the state being low when the return is actually high. So there's only good herds here, and if the return of the asset is low, then there is some possibility of complete learning. This would not happen without an info designer. So, are there any questions? Are there any questions? Okay. So let me talk about single disclosure. Here's a very simple rule. For every public belief which is outside the investment cascade, I'm gonna put posterior beliefs at the edges of the cascade set, right? And every time that the public belief is inside the investment cascade, I won't disclose any additional information. This is called single disclosure rule, because for every public belief outside cascade sets, all it takes is one message for the advisor to trigger herds from the outset. Okay, and note that with it, no investor actually learns from the past actions, because the belief dynamics is on cascade sets from the start. Okay, so there is no info externality here. So on the one hand, a single disclosure rule is always feasible, it's always base plausible, right? But on the other hand, because I have shown that the value function is concave and the belief process is a martingale, the expected value of the value function, it is always weakly lower than the value of not saying anything. Any distribution of posteriors must be weakly lower than the maximum distribution of posteriors that maximizes the investment probability. The literature calls it concavification of alpha. This is to say that the optimal value of information in this game is weakly lower than the value of information that the advisor could get by maximizing information today and somehow censoring information from the market. Intuitively, what I'm saying is that because the market never forgets, it's actually harming the advisor. And with these two inequalities, I can give a condition on the investment probability, which says when single disclosure is optimal. When single disclosure is optimal, it means that no information externality is optimal, right? But of course, I have to talk about the infrastructure only, because this is a primitive of the model, right? So pose the question, are there private infrastructures leading to single disclosure being optimal? And I'm going to make an assumption to have some structure about the investment probability, because it could be many things, right? So I'm going to assume that unconditional private belief density is log concave on the support. And technically, I'm going to assume that is also differentiable. I don't see this as quite restrictive because uniform distributions, normal distributions, if we truncate it to be an interval over 0, 1, beta distribution for a wide range of parameters, they are all log concave. And we use log concavity a lot in economics, right? But the log concavity allows me to put an interesting behavior in the investment probability. That is, the investment probability is going to be convex concave, which means that my problem now simplifies to finding a threshold, which could be at the investment cascade, but it could also be lower than the edge of the investment cascade, for which below the threshold, I'm going to be assertive in a sense that I'm going to induce posteriors 0 and this threshold. And above this threshold, I'm not saying anything. This means that it could be that the agents, it could be that the investors are choosing according to their private signals, and it could be that social learning is still going on. So suppose that the private beliefs are bounded. If the private beliefs are bounded and the density is log concave, then I might be able to give a complete characterization of when single disclosure is optimal. It depends on the right tail of the private belief density. If the private belief density is sufficiently fat, means that single disclosure is optimal. What is the way of understanding this theorem? Info externality will not be optimal if the contrarian private information is not rare. Why is that? Recall that the private belief is the private belief about the return being low. So if you have a lot of mass concentration of private beliefs being low, close to the support, close to the right bound of support, it means that contrarian private information against investment is actually quite common. When this is the case, the advisor would not like to take the chances of letting information going on, and it prefers to trigger informational cascades from the start. And just to give a visualization, my characterization allows me to define whether single disclosure is optimal in the uniform distribution case, depending only on how informative private information could be. This graphic shows when single disclosure is optimal. This one shows when single disclosure is not optimal. So log concave densities, they are bounded above, which means that as the private information structure becomes arbitrarily informative, the bound on the right tail should go to infinity, but this cannot happen. There can be no log concave density that satisfies it, which means that there will be a threshold over private beliefs, over public beliefs, sorry, for which the investment probability is strictly higher than the value of a single disclosure. So when the private beliefs are unbounded, there's always some room for information externality. Some degree of information externality is always optimal, right? I still have to tackle the question about information externality being at most a short-run phenomenon. So to do so, I rewrite the value of information for an advisor as just a probability measure of induced beliefs for each period. And because the public belief process converges, so it will converge the induced belief process, which means that eventually the expected investment probability must equal the long-run probability of public beliefs hitting the investment cascade. And with it, I might be able to prove that a very patient advisor might do well with a single disclosure policy. The optimal value function converges to the single disclosure value function as advisor becomes increasingly patient. This does not depend on the private information structure being log concave, being bounded or unbounded. So it's a quite general result. And the way of saying this is that the optimal social learning is mostly a short run phenomenon. So what I have done in this paper, I consider a stylized model between a financial advisor and investors. The advisor commits to a public information rule, but market never forgets the public information. And I pose the questions, how does it for designer change the dynamics of the market beliefs? Well, there is some social benefit because one of the informational cascades shrinks to a singleton. There is one state for which only good herds happen, and there is another state for which complete learn happens, even if private beliefs are bounded. And to which extent should the designer allow some info externality? If we consider private log concave private information structures, then I'll have a simple condition on the right table, which is about private information contrary to investment being rare or not. And I show that the optimal information externality is mostly a short-run phenomenon. Well, discussing crowd manipulation is not new to the literature at all, but many papers discuss taking the viewpoint of a benevolent designer, a designer that wants agents to truly know the state of the world. But there are very few that study dynamics when the principal and the agents, they have conflicting interests. When they do, they assume a lot of power for the designer, meaning that the designer might be able to censor information from the past and censor past messages as well. When they are not very restrictive, they usually don't tackle the question about the long-run effects of information. There are some papers that discuss optimal crowd manipulation, but considering multiple investors one period at a time. So it's more a coordination problem. So I analyze crowd manipulation through dynamic information disclosure. And because my model is somehow different from what has been done in the literature of the dynamic information disclosure, I extend some of the algorithms in this literature. Well, there are other results in this paper. It is very hard to actually characterize a value function and an optimal rule. I do so with discrete private information. I have a comparative statics talking about when information is going to be more or less informative when you change a little bit the discount factor, so it's not a long-run analysis. And I consider an extension in which investors do not observe the past realizations of messages. And I would be glad to talk about those extensions and all other results in the paper in this 2 minutes left that I have. Are there any questions? If there's not, I'm gonna stop sharing and we may conclude this section. We still have 1 minute.
Any questions? That's it.
Okay.
Thank you, Caio. Thank you, Ana. Thank you, Kazuhiro.
Thank
Very
you
much.
all.
Thank you
Thank you.
all. Felipe, do you end the section or should I do it?
I finished.
Okay.
Bye.